Let's talk about OpenMP tasks. We've talked about OpenMP sections. Remember, sections worked like this. You created a thread team, so Pragma OMP parallel sections. Anything that begins with Pragma OMP parallel creates the thread team. And then Pragma OMP section, singular, says peel off one of the threads and execute this. This can be multiple lines of code, could be a function call. Now here, and at the same time, peel off another thread and have it executing whatever is between these curly braces. Okay, and this works great. It's a nice way if you have different things going on in your code to give them to different threads. But you have to know how many of these separate tasks you have the moment that you type in the code. So here I'm assuming that there's only two things that I want put out on the threads because I had to type this in this way. What if you don't know? What if you say you want to set up threads to handle all the items, like one thread handling each item in a linked list? Well, you can't do that because with the moment you type in the code, you don't know how long your linked list is. All right. So sections are good for some things, but there needed to be something more. And so OpenMP created something called tasks. Okay, and this is fairly recent in OpenMP history. And here's the way I think about it. I think about it as I've got a package of Post-it notes, and I want to I want to have a bunch of things done. And so what I'm going to do is I'm going to write a description of a task on a Post-it note and slap it up on the whiteboard, and write another description on a Post-it note, slap it up on the whiteboard, and I'm going to get the threads to go attack those Post-it notes. And so each thread's going to grab one, and when it's done, it's going to go grab another, and when that one's done, it's going to go grab another. So the threads are all running simultaneously, but there's this common list of tasks on Post-it notes on the whiteboard, and each task is just grabbing the next one, grabbing the next one, grabbing the next one. Okay, that is OpenMP tasks. Okay, a task is a single line of code or a curly brace block. So when I say write down on the Post-it note, really what that is, it's a single line of code or it's a block of code. The new task could be executed immediately by the threads. It probably is, or at least the one that's not traipsing through the linked list. Or it could wait. Again, idiosyncrasies of the scheduler. The task could be executed immediately. There has to be an existing thread team for this to work. Okay, you can't just start the threads the moment you've got the Post-it notes up there. It seems like you should, but you can't. Um, Fire up the threads team, then start slapping up the Post-it notes. And again, the best uses I've found for this are things like processing all the elements in a linked list or a tree, something like that. Some sort of data structure where you don't know ahead of time how big it's going to be. And if you need to, you can create a barrier yourself, the OMP task weight. Okay, sections are static. It's whatever you typed in. Tasks are dynamic. You can create those Post-it notes on the fly. Okay, so let's do an example. Set number of threads to 2. Okay, Pragma OMP parallel. So at that moment, that becomes 2 threads. And I'm going to say Pragma OMP task, and I'm going to print the letter A. Pragma OMP task, I'm going to print the letter B. And, it's one line of code or it's code with curly braces around it. And so now I'm going to execute this. And when I do, I get that. Well, wait. One, why did I not get the same output each time? Well, okay. Idiosyncrasies of the scheduler. We already know that. But why did I get 4 things printed out when I only printed out 2? Okay. So yeah, the first answer is easy. It's because the order of execution is undefined. The second answer is that we asked two threads here. We created two threads and we slapped two tasks out there. And so both threads got each task. Well, that's not what we wanted. So how do we fix this? Here's what you do. This is a great use for that pragma OMP single. Okay, so right here, right after this OMP parallel pragma, we have two threads. Now at this moment, we have one thread. And so one thread is creating the post-it notes. Okay, both threads are eligible to execute the post-it notes, but only one thread is creating them. Whereas back here, both threads were creating the task. Both threads were writing on the post-it notes. That's why we had two post-it notes that said A and two that said B. But if we restrict it to a single thread, now only one thread. So one thread needs to write the post-it notes, but all threads can start plucking post-it notes off the wall and executing them. Okay, if you run this, the order of printing will still be non-deterministic. Most of the time, we don't care. We just want every post-it note to get processed and don't really care that much about what the order is. If you do, then you put a little task weight in between them. But you have to be careful because that really undermines your parallelism. So we love it when parallelism can just run flat out. We hate it when parallelism has to wait on another part of the parallelism. Okay, so here's a better example. This is the processing of a linked list. So pragma OMP parallel. Now we say OMP single, and we're going through the linked list. And so right here, pragma OMP task, we're saying process the element of the linked list where we are right now. So one thread is doing all of this. One thread is going through the linked list and slapping sort of the name or a pointer to each link on or each element of the list up on a post-it note. Okay, all threads are eligible to execute the post-it notes. So the other threads, even while the one thread is doing this, the other threads are out there plucking post-it notes off the wall. They've already started. Okay, this first private means it copies the current value of P into the task and makes it private. And you want that because this line of code is what's getting written onto the post-it note. Okay, we go to the next element in the linked list and so on. And now we have all the threads waiting here until all the post-it notes are processed. So this is how you would do that sort of thing. Let's do a tree traversal. Same idea. Okay, this is common in graph algorithms or sorting algorithms, things like that. You've seen these in like CS261. So strategy is let's follow one descendant node. So if I'm sitting at A, I'm going to go down to B. Then I'm going to go down to C, and we just go down the tree. We can rearrange this order, depending on if you're depth first or breadth first. That's okay. But here's what we're going to do. Pragma OMP parallel. Let's go single. And let's say traverse, and we're going to give it where to start traversing at. This is nice because we can make this recursive. That is, once we're down in the tree, we can say, oh, traverse starting here. That's what this is. This is traverse starting somewhere. Okay, so here's what traverse looks like. We're going to create a task with this line of code. So that's what gets written on the post-it note, except that it's filling in the pointer. Then we're going to create another post-it note that has this line of code written on it. And we're going to wait till those are done. And then we're going to do whatever processing needs to be done at the node we're at. And again, you can rearrange this if you want. So one thread is going to traipse through the whole binary tree, writing the post-it notes. And so we're assuming that the processing at each node is going to take a certain amount of time. Okay, otherwise, why would we want to parallelize it? So the traversing of the tree is pretty fast. And it's just writing down on a post-it note what it wants to have happen. And then that gets executed at some time by all the threads. Okay, so I did that and I created sort of some dummy thing to do. And this is the order, the way I coded it. This is the order that if I start traversing here, I'm going to go down and go down and go down. And so the first thing I'm actually going to process is H. So now I've written a post-it note with H's information on it. Then I'm going to come up here and go down. So this is the binary tree traversal I chose to use. Then we'll get this one. Then we'll come up here, but go down to here. So it's really a depth first kind of search. And what I was curious about is if I created 4 threads, how would it spread these 16 things to do onto 4 threads? Okay, using G++ 11.4, which is the default on Flip, here's what happened. And interestingly enough, thread 0 only did this one. And I think that's because thread 0 was the one traversing the tree. And so maybe it was too busy traversing the tree. Maybe I didn't put enough things to do here. I thought I had, but maybe not. If you forget that one red flag for 0, 1, 2, and 3 pretty much divvied everything up evenly. So, okay, and that's what should happen. So maybe 0 was traversing the tree and the other threads were running. And so by the time 0 got done traversing the tree, maybe the other threads had finished processing everything. I'm not sure. Okay, there's some options. Again, I was playing with options, but again, one thread I think got traversing the tree, not always thread 0. And the other threads kind of divvy things up evenly, which is what you want, which is really what you want to have happen. Although it would be nice if thread 2 could get involved in some of the processing as well, because I don't think traversing this tree really should have taken much time. Okay, so here's what happened. I created 6 levels of the tree, and this is with G++. And so thread 0 had one thing to do, and the other 3 pretty much divvied it up evenly. I changed it to 12, which is a lot more levels of the tree. And again, one thread had one thing to do, and the others had, well, pretty even still. Then I went to the Intel compiler and ran the same test. And here's what happened. This thread 0, well, one of the threads, I don't know which one, did the traversal of the tree and got involved in executing the post-it notes. And so you can see this is a really nice distribution of who's doing what. And then I cranked that to 12 levels and got this, and that's a really nice distribution. So it's really interesting. This is quite compiler specific. Yeah, playing with different options. Okay, performance versus number of threads. So here are different numbers of threads. Here are nodes processed per second. And these are the number of tree levels. And so I did 4 to 16. And you can see that, well, 16 is a big data set size. And you can see that for any number of threads, it really pays to have a bigger data set size. That is, as always, low data set sizes or low numbers of threads and low numbers of tree levels, the data set size, give you low performance. There just isn't enough there to keep the threads busy. So these are the kind of results I got. I think this gap in here is interesting, is going from 8 to 12. There's quite a increase in performance here, but not so much from 12 to 16. If you look at this, the 8-thread speed up is about 6.7, which gives us a 97% parallel fraction, which is great. And that's really nice. There is obviously some serial code in traversing the tree, but doing the processing, the parallel fraction was really high, which meant the maximum speed up could be as high as 33 times. If we crank up the size of the tree that we're processing. Okay, so here's the summary of the tasks. Tasks get spread among the current thread team. As you saw, GCC, G++ did not spread it out to the entire thread team, just to the thread team that wasn't doing any of the tree traversal. The tasks can execute immediately or they can be deferred. This is really part of the spec. The OpenMP spec says at some time, and it's up to the compiler writers to decide what that is. Tasks can actually be moved between threads. If one thread grabs some post-it notes and then has a backlog, other threads can come in and steal it. So internally, the management of the threads tries to even out the task assignment. And tasks are more dynamic than sections. With sections, you have to know when you're typing in the code how many divisions you want to create, whereas tasks, you can create them on the fly. So each has a specific role to play in OpenMP parallelism.